I think this next test is a very interesting test because we get to compare what we see with what we expected. And this can come into play a lot when you look at discrimination or representation. And we'll start with this example. So, first of all, as a teacher, we try to make sure all our students succeed regardless of race or ethnicity. We want everyone to do well, all right? Sometimes it doesn't feel like that, I know, but really, we do. All right. And we're frequently going to examine the statistics and say, hey, are we serving all of our different populations well? Is there anybody we need to check on? So the demographics for Cedar Ridge in 2013 and 14 are listed below. We had roughly 14.1% African American students, 5.8% Asians, 37.2% Hispanic, 37.6% white, and 5.3% other. Okay, it could be like American Indian, two or more races, a couple of other different populations. All right, now, it also in 2013 and 14, we had roughly 600 students take the World History EOC. And I wanted to look at the top quintile, the top performing students on the World History EOC at Cedar Ridge. Well, there are 122 students in the top quintile, the top 20%. All right. And I'm like, okay, were all of these populations properly represented among those top performing students? And we're going to use something called the chi-square goodness of fit test. So before we do that, we also want to make sure, what are we testing? What's our assumption going in? And if we change our mind, what are we changing our mind to? Well, goodness of fit means that we're checking if our sample is reasonably close to the model. So if I were to write a null hypothesis for our sample of top performing students, I would say that the ethnicities there should match the general population. And the way we could say it is the proportions of ethnicities among the top students matches the proportions of ethnicities for the entire student population. The alternate is, well, they don't all match. At least one is different. So, and that can be written very easily as saying at least one of the proportions is different from the model. So, first of all, it helps to look at the expected values. What is the model? If the model were true, that's our null, that the model is good, then what would we expect to see? So we're just going to take the proportion of the sample size for each category designated by the proposed distribution. Decimal values are fine for expected counts. So in this case, African American, we had roughly 14.1% African American students. If there are 122 top performing students on this test, we would expect to see 122 times 0.141 equals 17.202. All right. For Asians, we only had 5%, so that's like a third of that, roughly half to a third. About 7 Asians is how many we would expect to see. Roughly 45 Hispanics, based on the 30-some percentage, and almost 46 white students, and 6.5 of other. So that is what we expect to see if the null is true. All right. What did we actually see? Well, we actually saw 5 African American students instead of 17. We saw 12 Asians instead of 7. We saw 24 Hispanics instead of 45, 73 white students instead of 46, and 8 instead of 6.5 for other. All right. So, do you believe, looking at this data, that the different ethnicities are properly represented in the top quintile? I would actually like you to take a moment and write down what you think. I'm not going to give you something to write there. I want you to write. Okay, so how do we look at this analytically? We're going to come down to numbers. So luckily, it's the same test statistic, the chi-squared. It's the sum of the observed minus expected squared over expected. And I went ahead and calculated it here so you can see my 5 observed African American students minus 17.202 squared over the expected. And I did it for all categories. You can see I have 5 categories here, and I got 38.565. All right. But I also need to know degrees of freedom if I'm doing chi-squared. By the way, the same condition also applies for this distribution. All these expecteds have to be at least 5 or greater. Otherwise, our denominators can get too small and blow up the contribution. So we don't want the contribution to get too big just because of a small number there. So the next piece we need in order to do this analysis is something called the degrees of freedom. Now, technically, honestly, your calculator would do this, but it won't calculate your degrees of freedom. So if we only have one row or one column of data, it's just that size of that row or column minus 1. Or you could think of it as the categories minus 1. So there are your degrees of freedom. How many categories did we have? We had 5. So our degrees of freedom is 4. So how do we let the calculator do the work for us? First of all, you need the list set up of both your observed counts, which is pretty easy. You just put in what you see. The expected needs a little more work. You've got to go and calculate the proportion of what you expect to see, but that's not too bad. Then you press Stat and scroll to Test once you've got your list set up. And you're going to scroll to this one, chi-squared GOF test. Select list 1 for your observed counts. And now you can use a different list, but it's normally list 1. Make sure your expected counts is the next list, which it's normally list 2. Enter the degrees of freedom, which is basically your categories minus 1. Now, if you'd like to actually see the chi-squared distribution curve, all right, then select Draw instead of Calculate, but normally you're going to select Calculate. The output screen is going to show your test statistic, your p-value, and your degrees of freedom. So now let's go ahead and come to some conclusions. First of all, the goodness of fit test is always a right-tailed test because only larger values can lead to rejecting the null. Really small values, if the expected, first of all, if the expected is less than 5, we can't do it. But yeah, so our larger values are the ones that are going to contribute to the chi-squared sum. And looking here, my p-value is 8.57 times 10 to the minus 8. A lot of you, when that e to the minus 8 comes up, you're like, oh, the p-value is 8.57. It can't be bigger than 1. It's 8.57 times 10 to the minus 8. That minus 8 means I move the decimal over from this 8.57 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Now this probability is very low. So whenever I'm surprised by a very low probability, that's the only kind I find surprising, we reject the null. Which means we reject that the proportions among the top students is the same as in the general population. We actually have very strong evidence that at least one of the proportions is different.